Alright, this is our induction review, so we're going to start with Faraday's Law. Faraday's Law of Induction. What Faraday's Law says is that an induced EMF is going to be equal to the opposite of the change in magnetic flux over the change in time. So, all of the pieces to this, negative sign implies direction, so induced quantities resist the change in flux. That's one thing. And then there's this whole flux idea. Flux, just like electric flux, is magnetic field dotted with the area. There are a few instances where we actually have to do this integral. Most of the time, though, it's going to be B times A. The example that I'm thinking of with this is the loop above the wire. But past that, really, the area, the magnetic field and the area are constant with respect to each other. We're just looking how that changes in time. So, what we looked at before, I'm only going to do, I think, one of them, is let's say you have a loop of wire. Let's say you get really awesome at drawing and you make that loop of wire look 3D. We'll say it like that. And we'll say that this loop of wire has a magnetic field going through it that's pointing, well, in this direction, and let's say that magnetic field is decreasing. If that magnetic field is decreasing, then the change, well, that's pretty iffy. The change in flux over the change in time is going to be in the opposite direction of the magnetic field. And where we go with that, and why we need that, is because we can say that the induced magnetic field from the current in there is going to be in the opposite direction of this change in flux. And it's this little interaction in here that we call Lenz's law. Lenz's law only has one L. Lenz's law is the idea of the opposition to the change in flux. And so in order to get that induced magnetic field, we'll use one of our right-hand rules where we stick our right thumb in the direction of the induced magnetic field and our fingers wrap with the current. And so what we have with that is a current that goes that way or back into the page. And that's an induced current. So, the easy examples are where they tell you how the magnetic field changes, or they say, for example, I have a loop of radius r, magnetic field that's into the page, and the magnetic field is increasing as a function of time, so it's B0 plus CT, and I want to know what the induced EMF is at that point. So for this very simple example, the induced EMF is the change in that flux over the change in time. So looking at that, you have the change over the change in time, the magnetic field, B0 plus CT times the area, pi r squared. So, the only thing that is changing with time is this CT part of it. So, the derivative of B0 plus CT with respect to time is just C. So my induced EMF comes out to be C times pi times r squared. That's my induced EMF. If we wanted the current here, the current would just be that EMF, C pi r squared, over the over the resistance. And then looking at direction, we can see that the magnetic field is increasing as a function of time. So our our change in flux over the change in time is also into the page. And so we can say, we'll do it over here, that the induced magnetic field would be in that loop out of the page. So in order to make that happen, our induced current would have to be counterclockwise. Now, the next part of this is the induced electric field. So, in order to have a current, in order to have an EMF, there has to be an electric field that's providing the force for these charges to move. So, this is a different kind of electric field. Let's continue with this example over here. We're going to expand Faraday's law, and what we're going to say is the closed line integral of the electric field is equal to our EMF. And that EMF, we already said, was equal to the change in flux over the change in time, with the negative signs in there for Lenz's law. So looking at this, if we're looking at the electric field at the location of our wire, it's the electric field there times, well, tell you what, it's our electric field there, but the nature of this electric field is that it's constant at a given radius. This is a special electric field. It's gonna form little concentric circles. And the electric field is going to be constant at those concentric circles. It's a little bit different than the electric field that we looked at before that extended from charge to charge. This is a sort of a spatially bound circular electric field. So because the electric field is going to be constant at a given radius and the shape of my wire is a circle, I can pull it out and say that the electric field times this closed integral of dl is equal to that EMF that we just found. So continuing, the electric field times 2 pi r, that is the length around that thing, is equal to my induced EMF, which is c pi r squared. So we go ahead and solve that. And the electric field at that location is CR over 2. And that's as easy as it is to find the electric field location. Some things to say about this. That's kind of fun. Anytime that we have a change in the magnetic field, we also get an induced electric field. So the presence of this electric field does not depend on there being a wire loop there. This electric field happens all of the time. If I happen to put a wire there, then absolutely you will get an induced EMF. So the next thing that we're going to look at is motional EMF. And so the big example that we're looking at is, let's say we have a track, put a bar on that track. We have a length L here, that thing is moving with a velocity this way, and in the area we have a magnetic field, a constant magnetic field pointing out of the page. So this thing is going to move with a velocity, the magnetic field is pointing out of the page. There are lots of variations on this. We've looked at a ton of examples. One particular fun one is having a cart with a loop of wire on the top of it moving through a region of magnetic field. Another one was the tilted rail, where we looked at how these forces changed. But as this happens, we're going to look at it in two different ways. Way one, say that's B. The first way is just to say, okay, we've got our magnetic field, and we have a metal bar of length L, moving with the speed v through this magnetic field. Because there are charges inside of this metal rod and they can move, all the little negative charges in here experience, let's see if the velocity is that way and the magnetic field's out, all those little negative charges experience an upward force. So negative charges begin to gather up here at the top, but they stop when the voltage grows at the top, and so they don't go anymore. And so what we get is a nice little balance between, so we have a balance between the magnetic force and the electric force. And so with this magnetic force, it's just QVB, as you'll remember from the last chapter, and this electric force is just Q times the electric field, as you'll remember before. So just by the very fact that this thing is moving, we get an electric field inside of that rod that is equal to the velocity of the rod times the magnetic field. And if we remember that the electric field can be equal to our voltage divided by our length as we go across that rod, we'll see, if we plug that in here, V times the magnetic field is equal to the EMF over the length, and that BLV is equal to the EMF we get in that rod just by nature of the thing moving. Now there was a problem that we looked at that was very similar to this. It was the space shuttle problem. And if we allow these electrons to spray off this way and be taken in this way because of the direction that the force is pushing those electrons, what we see is a current in here that runs because of the magnetic field in this direction, remembering that our current is in the opposite direction of our flow of electrons. So let's see how that compares with approaching this same problem with Faraday's laws. So with Faraday's laws, we are primarily concerned with the change in flux. So our EMF is going to be change in flux over the change in time. So it's the change in our magnetic field, which is staying constant, times our area. In this case, our area is that length times that x dimension. Now the only thing that's changing in time is this x dimension here. And so the time derivative of that x position that we have is just the velocity. So from that, my magnetic field is B times L times V, which is the same thing. And again, if we wanted the current, it would be BLV over the resistance of the resistor in that circuit. I don't think I did that over there. And if we look at the direction, we'll do that in a different color. If we look at the direction, since that area is getting bigger, the change in flux, the change in time is with the magnetic field, since it's increasing. That means that my induced magnetic field would be into the page, and in order to get that to happen, I would have a current that runs clockwise. So from Faraday's law, that current would also be down in that bar and over this way and up through here. So we get a similar result either way we do this, and it's really nice to have things line up like that. Now, one more thing that we do need to remember for this is that once we have a current in this rod, it experiences a force. The force on that rod being the magnetic field times the length times the current. And we just solved for the current in both places, so the force on that rod is going to be the magnetic field times the length times BLV over our resistance. And so the force that this experiences is B squared L squared V over the resistance. And that force, by nature of things, is going to be in this backwards direction. So if we take that rod and we drop it down and allow the current to run through it, we could run into a case where we have a velocity-dependent force acting on something. And it's not uncommon for the AP people to ask that. So one of the things that we really do need to keep in mind with this is that at some point we may be in the unfortunate situation of saying, alright, the sum of my forces is equal to the mass times the acceleration. That's going to be equal to some constant force, maybe pulling it downward at an angle, like mg sine theta. Maybe it's just mg. Don't know what the nature of that is. Could be 0, minus our magnetic force. So m times dv over dt is that constant force minus b squared L squared v over r. And now we see the time dependent part of it, where we have our velocity here and our velocity here that we need to deal with. So we do a little separation of variables. And dv over f0 minus b squared L squared v over r. And that's equal to dt over m. We take our integral, which is super fun, and we get the natural log of, we go from 0 to t. We have to remember, if we start off at rest, it's 0 over here. If not, it's v0, just say 0 to v in this case. We get the natural log of f0 minus b squared L squared v over r. Divided by, when that's 0, f0, and that's equal to, well, not dt over m, sorry about that, and that's equal to t over m, but we can't forget that we also have to multiply this by 1 over the integral of all that, negative b squared L squared over r. And so you rearrange things, put e to the other side, and you can get that velocity as a function of time. It's one of the nastier things that you may have to deal with on this test. Okay, so that's going to be all we do the video over. We did a lot, I think, and you're very confident with LR circuits. We may go back before the AP exam and do a video on that, but I think for now we are good.